In the last few slides, we've seen how you can input boundary conditions in Fluent, but another important aspect of boundary conditions in CFD is where to locate the boundaries of the domain. There's a few general guidelines that can help with this. If possible, the inflow and outflow boundary locations should be selected so that the flow goes either in or out normal to the boundaries. This is not a mathematical requirement, but it typically results in better convergence of the simulation. You should not observe large gradients in the direction normal to a boundary. This could indicate a problem in the setup somewhere, or it could indicate that you need to move the boundary further upstream or downstream such that it's located away from the gradients. Finally, it's not desirable to have skewed cells near the boundary. Skewed cells introduce mathematical errors, and being in proximity to the boundary then helps to propagate those errors into the interior of the domain. In many cases, there can be more than one choice for where to locate the boundaries of the computational domain. The picture here shows one such example. The application is a combustion chamber. Air flows through a supply pipe into a manifold and then into a nozzle. Fuel is introduced into the nozzle through a separate supply pipe. The air and the fuel mix, and then the air-fuel mixture enters the chamber and combustion takes place. So in this system, you could consider three possible locations for the inlet boundaries. The first location, which is shown in red, is to put the boundaries upstream of the manifold and upstream of the nozzle. The advantage of doing this is that the air and fuel streams are separate, and you can also use uniform profiles for velocity and turbulence, because the velocity and turbulence profiles will develop naturally as the solution is solved in the supply pipes. One thing to consider about this boundary location is that possibly because these are located further away from the area of interest, which is the combustion, that the more cells might be required in the computational mesh. The second choice, which is shown here in yellow, is to use a plane that passes through the supply pipe and through the nozzle. At this location, the air and the fuel are still separated, which is beneficial, but it would require accurate velocity and turbulence profiles, because without the accurate profiles here, the solution won't be able to correctly predict the mixing here, and then subsequently it can't accurately predict the combustion. So in order to be able to place your inlet at location number 2, you do have to have accurate velocity profile data. The third choice you could consider is location number 3, which is shown in green, and this is the nozzle outlet plane. Here you need to have lots of accurate experimental data, not just about the velocity and turbulence profiles, but also about the mass fraction profiles because the streams have mixed. So if you have experimental data for these values, then you can move the inlet to this location and specify the accurate data. But for cases where you don't know about the profiles, then location number 1 would probably be the best choice. Another guideline to specifying well-posed boundary conditions is that outlet boundaries should be located downstream of any recirculation zones. Specifically, you'd like it to be located far enough downstream that the flow can redevelop again after the circulation. This makes it easier to specify accurate boundary conditions. It's bad for a boundary to be located across a recirculating zone because it's difficult or impossible to apply the right backflow conditions. If you ever do encounter a situation like you see in the image here, the best course of action is to return to the preprocessor and extend the domain much further downstream. Many CFD simulations are performed using models that have a single inlet and a single outlet. In cases like this, the most robust possible combination of boundary conditions is to use a velocity inlet and a pressure outlet. This is valid for incompressible flows. If you're solving a compressible flow, then you can use a combination of mass flow inlet and pressure outlet, and this is also robust, and you can use this for an incompressible flow as well if you're specifying the mass flow. Problems where the total pressure is specified at the inlet and the static pressure at the outlet So in other words, you have a pressure inlet and a pressure outlet boundary. These are well-posed problems, but they may be sensitive to the initial guess. In this situation here, we prescribe the pressure drop across the system, and the CFD calculation tells us the mass flow rate corresponding to the pressure drop that we prescribed. In the upper two cases, the exact opposite happens. We specify the mass flow rate through the system, and the CFD calculation tells us the pressure difference that needs to be applied in order to achieve that mass flow rate. At the bottom, the combination of pressure inlet and outflow should never be used because the static pressure level is not fixed. This applies to both incompressible and to compressible flows. If you're solving a compressible flow, the combination of mass flow inlet and outflow should not be used because outflow is not compatible with compressible flow boundaries, but this combination is okay if you're using a constant density fluid. Finally, you can specify negative velocities at outlets, but if you have a system with only one inlet and one outlet, when you specify the velocity at both boundaries, it can make the system numerically unstable, and normally you want to avoid doing this. Turbulence levels must be specified at all inlets and also anywhere there's backflow. This will be addressed in more detail in Lecture 7, but there are a few quick guidelines that we can provide here. If you have absolutely no idea, the following parameters are good for general use, which is to choose intensity and viscosity ratio as the option, and use values of 5% intensity and eddy viscosity ratio equal to 10. For most physical flows, turbulence intensities range from about 1% to 5%, but it does depend on your specific application. The values that we see here are sufficient for nominal turbulence through a circular inlet, and they're good estimates in the absence of any experimental data. In situations where the turbulence is generated by wall friction, you should consider extending the domain upstream to allow the walls to generate the turbulence and the turbulent profiles to become fully developed. And as we mentioned before, this will be discussed in more details in Lecture 7. On one of the earlier slides, it was noted that in order to use symmetry boundaries, both the geometry and the flow need to be symmetric. This slide shows an example of a case where the geometry is symmetric but the flow behavior is asymmetric. The phenomenon is known as the Coanda effect. And what happens is, when a submerged jet exhausts into a sudden expansion, above a certain Reynolds number, the jet will tend to deflect to one side or the other and attach itself to the wall. Physically what happens is, initially instabilities in the jet cause it to turn towards one wall or the other, and when that happens, the entrainment of the fluid on the side of the jet towards which it's pointing is restricted. Because of the geometry, the jet cannot entrain as much fluid on that side, and so what that does is it creates a suction force and a pressure difference develops across the jet which causes it to remain stuck to the wall. If a symmetry plane is used in the model, then it's not possible for the numerical simulation to pick up the Coanda effect. When you simulate an object located in an external flow, and the height of the object is h, and the width of the object in the plane normal to the flow is w, then the following guidelines are recommended for the minimum size of the computational domain. The height should be at least 5h, and the width should be at least 10w. Upstream of the object, the distance should be at least 2h, and downstream of the object, the distance should be at least 10h. In cases like this, the wake can extend far downstream, so it's important for the downstream boundary to be further away and to have good grid resolution throughout the wake region. You also want to verify through post-processing that there's no significant pressure gradients normal to any of the boundaries in the computational domain. If there are, it indicates that the boundaries are probably too close to the object and are influencing the solution there, so it's recommended to enlarge the size of the domain and repeat the calculation. So that wraps things up. In this lecture, we've seen that cell zones are used to assign which fluid or solid materials exist in a region, and options exist to specify cell zones as porous media or laminar regions, to fix values and apply source terms, and also to define zone rotation. Boundary conditions are assigned on boundary zones, and this can include both internal and external boundaries. We have gone through the most commonly used boundary types and described the types of inputs that are required for each of them. Finally, locations and types of boundary condition are also extremely important for good convergence and accurate results, and we reviewed a number of guidelines related to boundary locations and different combinations of boundary types.